Example 3 in 4.2 talks about adding or subtracting to create a new function. So they give us this function as the final one, and then they ask us to break it up into 3 different functions that would have added to that one. Now, in your book, they're kind of lame about it. They go, oh, well, f of x could be x squared, g of x could be negative 2x, n of x could be positive 3. You add them up, and there you go. That's all well and good, but really, n of x equals 3? That's not a function, that's just a number. So what I would prefer to see you do, and what I'm going to insist on the open book test at the end of this chapter, is that you always include x in your function. So what we could do there is, it doesn't matter how we break it up, as long as we're able to combine all the like terms and get where we want to go. So for example, and you won't have the same answer for this, but all I need is that to be the final one. So I could write that f of x is actually x squared plus 1, for example. And then I could write that g of x is negative x plus 1. And for my final, n of x, I could write that this one is negative x plus 1. Then, if I were to take all of these and combine them, I would have x squared plus 1 plus negative x plus 1, which I can just write straight up like that, and another negative x plus 1. Doesn't matter if they're the same, that's fine. Now, when I go to simplify this, I look for my like terms. X squared's by itself, there's nothing like it. There's a negative x and a negative x, which gives me negative 2x. There's a positive 1, a positive 1, and a positive 1, which gives me positive 3. So you see that this is a combination of all of those, and it gets me to where I need to go with x squared minus 2x plus 3. Without being all boring and just writing a number down for a function. So I prefer, if you avoid writing a number for a function, level it up just a little bit and pick apart the equation so that each of your individual functions has an x in it.